Okay, so I'm delaying your lunch, so let me skip straight to the main points that I'm going to make in my talk, in case if you decide to kind of drop out nice and early. I'm going to talk about magnetic resonance searches and how they use searches for axion-like dark matter and how they use spin ensembles as transducers and why that allows us some extra flexibility to maximize sensitivity of our searches. I'm going to talk a little bit about a first generation of CASPEr searches and the fact that they're currently operating at the design sensitivity, and in the future what we're doing, or currently what we're doing, and in the near future we're hoping to achieve quantum limited sensitivity at the level of the spin projection noise. And I'll make a point that with this level of sensitivity, at least with CASPEr electric experiment, we can actually get down to the QCD axion band if it's at about 10 centimeter scale. And I'll talk a little bit about spin squeezing and how this may allow us to reach the QCD axion band with even a smaller experiment. So the promise I wanted to make is that if you do stick around till the end of my talk, I will remind you of some very basic rules of quantum theory that you probably learned many years ago in your first quantum mechanics class. And I will suggest a potential route to break these rules. Okay, so I am of course not the first axion, not the first one to talk about axions at this conference. So here's my first kind of starting point slide. They solve the strong CP, QCD axion solves a strong CP problem. Axions and axion-like particles arise naturally in theories of physics at high energies when symmetries are broken at high energy scales. And of course, axions and axion-like particles are good dark matter candidates with kind of to a good approximation the axion field varying harmonically at some axion Compton frequency. Most of the talks and most of the experiments have focused on the interactions of axion-like particles with photons, which is written over here on the left. However, there are two other possible interactions. Actually, the defining QCD axion interaction is the interaction with gluons, which is written over here. And to those of us who are kind of not too into high energy theory and prefer just normal non-relativistic Hamiltonians, this looks like a nuclear spin that interacts with an oscillating electric dipole moment, which is induced by this axion field in presence of an effective electric field. And of course, the third interaction is the gradient interaction of the gradient of the axion field, for example, with nuclear spin, or of course with electron spins or any fermion spins for that matter. As I said, most experiments have focused on the electromagnetic interaction for reasons that I'll mention in a little while. However, there's of course many experiments, several experiments that look at the interaction with leptons, and there's a few that look at the interaction with gluons. In my talk, I will focus on these two interactions, and I'll talk about the CASPEr electric and the CASPEr gradient experiments a little bit. Before I do that, I wanted to introduce just some concept of magnetic resonance. For those of us who don't do this every day, has anyone ever been inside one of these things? Ooh, okay, a lot of people, great. So this is an MRI machine, of course, and it's an MRI scanner, and a lot of hospitals and research institutions around the world have these. I think there's about 25,000 of these around the world. And of course, it's a very powerful tool for non-invasive imaging. You don't have to take a scalpel and cut your elbow or your shoulder. You can just look inside. How does this work? So the simplest system to do magnetic resonance is a spin a half, which is written over here as a nuclear spin I. There's no dark matter here. You have some nuclear gyromagnetic ratio, and we have this interaction Hamiltonian. This is just the Zeeman interaction, again, that you probably did in your first or second quantum mechanics class. If you take a spin a half and you apply a constant bias magnetic field B0, and a radio frequency magnetic field that oscillates at some frequency omega 0, then this Hamiltonian breaks up into these two terms. Here's your constant bias field, here's your RF field. So you have the spin 1/2, it's sitting in this external bias field. That bias field splits the spin states into spin up and spin down. And then any self-respecting spin 1/2 will want to go and sit in the ground state. So the sample will magnetize, and there'll be an excess of spins down here in the ground state. In other words, there'll be some magnetization of the sample. So now, if I match the frequency of my RF field omega 0 to the spin splitting, now this radio frequency field can flip spins. What this will look like is the magnetization tilting. When it tilts, it will precess at the Lamour frequency. And now I will place some kind of a magnetometer, a sensor, right next to my sample, or couple it to the sample somehow. It could be a coil. And then this will just detect, because this magnetization precesses, this sensor is sensitive to the transverse component, which oscillates at a Lamour frequency. So I'll see a nice signal at that Lamour frequency. Again, this is a ubiquitous tool for non-invasive imaging and studying molecular structure. So that's magnetic resonance in a nutshell, in one slide. Let me go back to Axions, now introduced as dark matter, and I wrote down these two Hamiltonians. This is the EDM interaction Hamiltonian and the gradient interaction. Here I'm focusing on the gradient interaction with nuclear spins, I. And of course, these interactions occur with the axion or axion-like particle dark matter field that oscillates, so I can just basically plug that in. And when I do that, well, I get something like this. So I just plug in this A into either here or here, and I get something that looks like one of these two Hamiltonians. A lot of letters there, but the thing that counts is that it looks like something that oscillates times nuclear spin. So to a nuclear spin, this looks like an oscillating radio frequency magnetic field. It's not a real magnetic field because it doesn't obey Maxwell's equations. It's not currents that are sourcing this magnetic field. That's why there's a star there. It's sourced by this axion-like dark matter field. However, the spin doesn't care. It just sees an energy shift. So let me go back to my slide about magnetic resonance. So here is my Hamiltonian of this nuclear spin oscillating with the dark matter axion-like field. And I will still apply a constant bias magnetic field, so this will give me this first term, but now I will not apply an RF field. I will just leave this Hamiltonian right there. So once again, I have a spin 1/2 in this constant bias field, spin states split. The spins like to sit over here in the ground state, so the sample will magnetize along the magnetic field. And now if I get really, really lucky, and the frequency omega A, the Compton frequency of the axion-like dark matter field, matches the spin splitting over here, there'll be a resonance. And now this interaction Hamiltonian can flip the spins. In other words, this magnetization will tilt and precess, and I will, of course, place a magnetic, some kind of a sensor, couple it to my sample, and so now my sensor will show up. What will show up in my sensor, despite the fact that I haven't applied any radio frequency field, what will show up is a nice peak at the Lamour frequency, which now matches this Compton frequency of axion-like dark matter. Of course, we don't know what that frequency is, so we have to search for that by scanning our applied bias magnetic field B0. We sweep that, and we look for this little bump that pops up. So in other words, CASPEr or any magnetic resonance search, or not any, I should be careful here, at least the kind of CASPEr idea of the magnetic resonance search for axion-like dark matter is basically a magnetic resonance experiment where you do not apply a radio frequency field to flip the spins. You let the axion-like dark matter do that for you. So here's kind of a very simplified version of what I just said. You have your axion-like dark matter, and now if you were looking for the electromagnetic interaction, you would just have some kind of an electromagnetic sensor that that couples to this axion-like dark matter field. But now you have an extra transducer. You have the spin ensemble that actually couples to this axion-like dark matter and generates this electromagnetic field. Why bother? Because if you just have the electromagnetic interaction, well, there's a few parameters that people have talked about that you can optimize: magnetic field, volume, sensitivity, and so on. But now, because we have this extra transducer, what this lets us do is actually play around with a lot of parameters here of this spin ensemble that allow us to optimize the efficiency of this transduction and therefore maximize our sensitivity to axion-like dark matter. We have a few more knobs, and that's nice. Okay, so I'm supposed to talk, present slides, and you guys are supposed to ask questions, but I'm going to turn the tables a little bit, and I'm going to ask a question to you. And again, you may have been asked this on your first quantum exam. So if you have a spin a half, a single spin a half, a very simple system, and you prepare it to point along the magnetic field along the z-axis, or the z-axis for the non-Americans, and then you measure the transverse component of that magnetic field, what will you get? What can you get? Thank you. Plus or minus half. Excellent. So there's one person over here. What's that? One person passed quantum mechanics. Thank you. Yes, that is correct. Plus or minus a half is are the only two options you have with a spin a half. You cannot get zero. And so what that means is that if you measure a bunch of these spins, if you either measure the spin a bunch of times independently, or if you have a bunch of independent spins, you will get on average zero, of course, once you average a bunch of measurements, but there'll be a distribution. And the width of that distribution will be square root of the number of averages or of the number of spins, and square root of n. And this is known as a spin projection noise, which is the standard quantum limit for measuring transverse spin projection. And of course, Felix Bloch wrote about this in 1946. What does this mean is that for our experiment over here, if we don't do anything, if there's no dark matter, no anything, we just sit there, we prepare them, we magnetize them along the z direction, and then we measure the transverse projection, there will still be some kind of a signal at the Lamore frequency. And the magnitude of the signal will be proportional to square root of the number of spins in our spin ensemble. In other words, the standard quantum limit for measuring the transverse magnetization is proportional to 1 over the square root of the number of spins in my sample. It's the best I can do to measure the angle there of the tilt. This is the SQL, the standard quantum limit, and of course this has been detected in many NMR experiments. Here are some, as far back as 1980s. That's not a problem. However, I'd like to ask a question: how to build? How do you, if you cared, and if you wanted to do this, how does one build an NMR experiment with sensitivity limited by the spin projection noise? I'm glad you asked. So here is my, so I have a couple of slides with some circuits over here. Here is my NMR experiment. And actually, there's no NMR experiment yet. It's just the resonance circuit. So I'm considering a resonance circuit over here that's coupled to an amplifier, and it's one of these magic noiseless amplifiers. There's no noise in my amplifier. The only noise in my circuit comes from the resistance of this, the intrinsic resistance in the resonant circuit that I couple. So here is the circuit noise, and that's the Johnson noise. So I can write down the spectral density of that noise is proportional to the resistance and the circuit temperature. And that's just a flat line, circuit Johnson noise. So now I insert a spin sample into my coil. So now the spin sample modifies the inductance and the resistance of my coil, and also adds a little bit of extra noise to my circuit. That noise is exactly the spin projection noise. So when I write down that spin projection noise, I can write it down in terms of an effective circuit resistance. That's due to the spins, so there's a little spin resistance and a spin temperature. I can write that down. I can write that down in terms of a bunch of spin parameters. It doesn't really matter what the details are. If you care, there's a paper right here where we analyze this in quite a bit of detail. However, the circuit Johnson noise is here in blue, and the spin projection noise is peaked around the Lamore frequency because of this resonance over here. That's in red. And the total noise is, of course, here in green. So now, in order to build an experiment that's limited by my spin projection noise rather than the circuit Johnson noise, I need basically this blue to be below this peak, this red peak over here. That's my condition. And if I write that down, you could write that down in terms of a bunch of parameters. And then I could ask, okay, what about the actual CASPEr experiments that we're building at Mainz and Boston University? What does this all mean? I'll plug in a bunch of numbers, and at Mainz, this means that we have to cool our experiments to about 20 Kelvin and have a quality factor of better than about 3,000. And here is an experiment, of course, of CASPEr gradient at Mainz. There's some group members down there. So that's using xenon in an NMR apparatus and a high homogeneity magnet. And for CASPEr electric at Boston University, if I plug in the numbers, what I get is that my circuit temperature has to be better than about 50 millikelvin, colder than, or we can get it to about 50 millikelvin, and the quality factor has better than about 30,000. So here is our team at Boston University with the Blue Forest Dill fridge, where we are building exactly this experiment. And actually, one thing I wanted to mention is that we haven't yet done this, but we've done a bunch of non-resonant searches which are operating exactly at design sensitivity. And what we're doing now is we're building a resonance search, which is aiming, if we can achieve this quantum spin projection noise, we can basically demonstrate that provided we scale our sample up to about 10 centimeters or so, we can reach the QCD axion band. Let me return to this slide very quickly because our chair is telling me that it's time to go. So here is my, again, my single spin a half, or maybe independent, many independent spin a half, and here is my spin projection noise over here. I will show this as a little circle over here on the so I'll plot, if I plot the transverse spin components, there'll be a little circle. So what I could do, and it's possible to do this, we think we know how to do this, is we can squeeze the spins in our sample. In other words, you can't do anything about the total area of the circle, but you can squeeze it in one direction. And if you do that, what you'll see is that in the squeezed direction, your distribution narrows. Therefore, your sensitivity becomes better than the quantum spin projection noise, and maybe we can even get better than the standard quantum limit. So let me wrap up. This is my summary slide. I've talked about the magnetic resonance searches, which focus on these two interactions of axion-like dark matter. I've talked about how this focusing on these interactions allows us to have some flexibility. And I haven't talked about the details here, but there will be a talk tomorrow that will address some of this. We're currently operating at projected sensitivity that's limited by thermal spin polarization and sensor noise. We're working towards moving over here towards the quantum limits. And with a 10 centimeter scale sample, we may reach the QCD axion, and spin squeezing may allow us to do this with even smaller samples. So before I wrap up, I wanted to express gratitude to the Patras organizers. Not only is this conference being very smoothly run and being very scientifically stimulating, but it's also great fun. I do recommend a lab tour. You may find Axions. Thank you.
Thank you very much for this very interactive, great talk. We have a few, not a lot, but a little bit of time for questions.
Congratulations.
Thank you.
Great talk. How do you squeeze the spin?
Excellent question. You've noticed that I did not talk about it. Yes, the brief answer is that we can squeeze the spin by coupling it to a high quality factor resonator that I talked about a little bit, and modulating that coupling at twice the Lamore frequency. We're writing up that paper right now, but if you'd like to get the details, I'll be more than happy to discuss afterwards.
One more question over there.
Hi, great talk. So is the only difference between CASPEr electric and gradient that you apply some electric field in electric? And also, you have this star that you said was like an effective electric field. What's effective about it?
Excellent question. Thank you for asking that. And indeed, I did not address any of that at all. Hendrik may talk about this a little bit tomorrow. So this is an effective electric field in the same sense that this kind of, it doesn't obey Maxwell's equations. It's not a real electric field. It's actually just a way to encode the energy shift of this nuclear spin when it's experiencing this kind of interaction with this oscillating oscillating electric dipole moment, dn. So it's basically a way, let me go back over here. Well, it's a way to quantify the size of this interaction over here. So it's not, again, it's not an electric field. Because it doesn't obey Maxwell's equations. It's an energy shift. It's a quantity that has units of electric field. But what this means is this experiment, because you asked what's the difference, this experiment has to use uses solid samples, so we can have this. In a liquid, this would be averaged to 0. CASPEr gradient likes to use liquids because then you can get narrower lines.
Okay, thank you.